Yes, welcome to Easy Gates TRB Polytechnic ECE Solutions video session. Let us get into the next problem and hope you are able to sense the level of the questions raised by TRB. Okay, so if you really learned your subject and you might have enjoyed attempting all the questions, okay, and appreciated the work of the TRB. Yes, I am able to sense that. Okay, as I suggested in the past videos. Okay, yes, you see the pulse of TRB. Okay, so they raise the bar and only by raising the level of the questions. Okay, yes. So not all the questions in that standard. Okay, some questions like this. Okay, straight away connecting to the logic. Okay, so straight away we'll get the answer for this kind of problems. Yes, okay, so let me offer the answer key for this. The Thevenin's impedance is found. Thevenin's impedance is found. That means Thevenin's impedance, either you can call it as Z Thevenin. If it is a purely resistive circuit, you can call it as a R Thevenin of a circuit or network. Okay, how to find the Thevenin's impedance means the first condition of, as per the principle of Thevenin's, any circuit can be simplified or Thevenized into a single voltage source and single impedance or resistance. If it is AC circuit, you call it as impedance. If it is a DC circuit, you can call it as a resistance. So let me say it's Z Thevenin and this is V Thevenin. V Thevenin is a open circuit voltage. And what about Z Thevenin means it's a source free resistance of the circuit. Okay, source free resistance or impedance of the circuit. That means you need to switch off all the sources. Okay, only what sources? Dependent, independent sources, not dependent sources. You have to make your circuit source free. You have to switch off only independent sources. If there are dependent sources, you have to keep them active in the circuit. Then, what is the condition? So we have a circuit. This is the circuit. Okay, so the whole circuit, I have the circuit has some elements and sources in this, and there are two terminals of the circuit where the load will be connected, usually for getting the response. Okay, that's a load. It can be an AC load or DC load. Let me shortly call it as an impedance, load impedance, so that the statement is universal, applicable for both DC and AC. So I connect a load here. Okay, the load is connected between the two terminals. Okay, so the point is you need to calculate your Z Thevenin. Yes, how you will calculate Z Thevenin? Z Thevenin is only to find the response in the load. So wherever you want to find the response, disconnect that element from the circuit. Disconnect that element from the circuit. You can label the terminals A and B. And from A and B, you are looking for both V Thevenin and Z Thevenin. That's a basic. Okay. Yes, now let me see what he's talking about with respect to Z Thevenin by shorting the given two terminals. Okay, we don't short by connecting load across the given two terminals. No, we are disconnecting the load across the two given terminals. Okay, between any two open terminals. No, it's not between any two. It's not between any two open terminals. Between the given two terminals open. So given two terminals means A and B. Okay, these are the given terminals. That's where you need to get the Thevenin's equivalent. Given two terminals, you can go for the Thevenin's equivalent, not between any two open terminals. So the best choice is option D. A simple problem talking about impedance, Thevenin's impedance. Okay, that's easy. So the another important point I want to convey here is this is a circuit. So you can find impedance of a circuit. It may be tuned. Okay, so you are looking for this impedance is that Thevenin means you can happily apply a potential, but for that first you have to switch off all the sources here. Switch off all the sources in the given circuit. Switch off them. Then apply a known potential. This will be helping you. Maybe you can make a problem like this. Some potential you can excite the entire circuit as called Vx and look for the current Ix. Sometimes this will be useful. That's what we call as is a Thevenin between A and B. So it's anyway the open circuit. Okay, terminal impedance only. So any circuit excited by a voltage Vx, if that is drawing a current of Ix, then Vx by Ix will give us what? Is a Thevenin's. That's anyway another fundamental of Vx, Z Thevenin, which can be exploited especially when the circuit is having dependent sources. Okay, that is also another fundamental of Z Thevenin. And he's not talking about this, he's talking about this only. Okay, this is how a practical observation of Z Thevenin will be done, and this is for the analytical stuff. Okay. Fine. So anyway, the right answer is option D for this problem. And probably every GATE aspirant with a little basic of subjects might have given a right answer for this. Okay, that's my guess. Hope so. And the next problem from control systems. Again, it's steady state error. Already I have given a fundamental for steady state error in one of the earlier videos. There is a first problem. Okay, probably I started with acceleration error constant. Okay, exploit the same fundamental here, but there the input is parabolic. Here the input is step input. But given the type of the system means, okay, type is always referred. So take the closed loop structure once again. What we have is the input command R of S in Laplace domain. Then in the forward path, we have G of S. Then in the feedback path, we have H of S. Output is C of S. So the focus is on the steady state error. Okay, at this point, that's output of the summing point. As per the steady state error concept, what is type of a system means? It's type of G of S, H of S only. It's not type of the closed loop transfer function. Type number means type of the loop transfer function only. So what is the type number of G of S, H of S? Type number of G of S, H of S is nothing but number of integrators in G of S, H of S. So we have how many integrators in our loop transfer function? Number of integrators only responsible to make the error zero. For example, if we have step input, you need minimum one integrator to make the error zero. That's a concept. If you have a ramp input, then you need minimum two integrators to make the error zero. If you apply a parabolic command, then you need minimum three integrators to make the error zero. Otherwise, if you are short of one integrator short, error will become a constant. Okay, so suppose if we have no integrator for a step input, you apply a step input, but we have zero integrator means error will become your step size by 1 plus kp. Step size by A is a step size here. Suppose if you apply a ramp input, but one short here means zero integrator, no integrator system, error will be finite. Okay, for a step input. If you give a ramp input, but one short of this minimum requirement, two integrator, one integrator means error will be finite. That is going to be A by the velocity error constant kv, because it's a velocity command. Then already we played with the acceleration command. So 3 is a minimum requirement. If you are one short, okay, so you have only two integrator means error will become A divided by K, A acceleration error constant. This is how the logic goes. Okay, so what we have is a steady state error due to unit step input, but it's a type 0 system. Already I said type number of G of S, H of S is nothing but number of integrators. So when type is 0, we have 0 integrator means that's your error. It will be A by 1 plus Kp, where Kp is the positional error constant, like acceleration, velocity, error constants. It's a positional error constant. So the command is known as position command. The step input known as position command. So it's error constant. We call it as positional error constant, Kp. And that's a standard expression, universal expression, A by 1 plus Kp. A is a step size or the step magnitude. What is the step magnitude? Here it is unit step. So A is equal to 1. Therefore, the answer is yes, you can pick the answer. Such a simple problem. Okay, so once you know the fundamental, straight away you know the answer. Maybe by habit you will remember this. Okay, so straight away people will give the answer by within 20 seconds. Okay, you can read and complete this kind of problems. Okay, that is the correct answer. Okay, 1 by 1 plus Kp. So type 0 error exists, type 1 error is 0. So going by this logic. Okay, so given the logic for minimum integrator, step input minimum one integrator, there is a type 1. Okay, so step means type 1 is the minimum requirement. Type 2 ramp input, okay, it will be 0. It's a minimum numbers I'm talking about. You're giving step input, you have two integrator means yes, you have more than sufficient number of integrators means still error will be equal to 0. What I'm talking about is minimum number of integrators. So ramp input minimum you need two integrators, minimum type 2 system. A parabolic input minimum type 3 system to make the error 0. If one short, error will be there. Two short, see what happens. Okay, you go by the concept of steady state error analysis. You know that ESS is equal to limit S tends to 0 S into E of S. Okay, already you know E of S by R of S is your transfer function as a function of the loop transfer function G of S, H of S. Okay, yes, you can try. So that's an easy problem for 1 mark. So most of them, okay, might have given a correct answer for this. Next one. See, there is a link between this problem and this problem. Because, okay, so the statement is not talking about that link. Okay, so it is talking about something related to the steady state error somewhere. Okay, so yes, integral control action. Yes, you got the clarity needed in the last problem itself. Since I said I need integrator in the loop. Okay, either you have to have that integrator in the forward path or in the feedback path. Usually we prefer unity feedback. So always we place the integrator only in the forward path. So that is exactly your controller. If the system is not having sufficient integrators, we can use the integral control action all to make error 0. That's a goal. Okay, or role given to the integral control action. So the proportional action as its role, integral action as its role, derivative action as its role. P is actually to control overall speed. That's why we use a BID in a closed loop control system. This is going to take care of overall speed of the closed loop control system. This is going to take care of overall steady state response of the closed loop control system. This is going to take care of overall steady state response of the control system. Its job is ultimately to make the error 0. That's an integral action. Whenever you want error 0, you can happily use integral control action. Then derivative, integral and derivative are quite opposite to each other. So this is going to take care of transient performance. If you want improved transient performance, you have to add the derivative action. So transient response. Okay. So integral takes care of steady state response. Derivative is going to take care of transient response. As of now, advantage of integral controller means, say for example, I have a step input. Now it's well connected to the last problem. I have a step input. Okay, in my closed loop control system, negative feedback, of course, I have G of S. Okay, so then H of S. So this is the output. I'm talking about the error now. So it's up to you to focus either on the output or error. So as of now, I'm focusing on error because I already played with the steady state error concept. I'm applying a step input. So now if type is, that is, if G of S, H of S, G of S, H of S as 0 integrators, then definitely error will be finite. Then only we should think of adding an integral action using a controller here. That's a controller place. Okay, so add pure. Usually we don't go for a pure integral action, but he's talking about the role of integral control action. By default, we go with a P, PI, PD, or PID. The moment you start using I, you have to go strictly with the PI controller. That's a rule of thumb in control system. So strictly we have to use PI. But what is the role given to I means? So if you make a PI, then G of S, H of S will have one integrator. That integrator is enough to make the error 0 as per the concept of steady state error. Yes. So you need to ensure one integrator, then error will be automatically 0 for a step input. But here it's not talking about step input and all. Okay, that's how you need to understand. So the role given to integral action is to improve the steady state performance or response. So ESS has to be made 0 for the given situation. So the point is, if integral action is not there, means only proportional alone is there. Proportional alone, if error is not brought down to 0, usually proportional alone won't, assume it's a type 0 system. You have only proportional controller. You can reduce the error, but you can't completely eliminate the error. If you want to eliminate the error, then you have to use only integral action along with the proportional. So instead of P resulting in finite steady state error means, so use PI, immediately the error will become 0. So here error will be finite. Yes, that's how the problem has to be perceived. Those who know already this straight away can give the answer. Yes, now you can sense the answer. The role of I is always, okay, to eliminate the steady state error, to make the error 0. Eliminate steady state error. Okay, error is 0. So actually, it is resetting the steady state error because of that integral action, sometimes also known as reset control action. Maybe that's another name of integral control action. It's also known as reset control action. Its job is to reset the error. Okay, so but as I said, the demand of integrator is okay, so more than one depending on your input command. Okay, so if the system is if system doesn't have enough number of integrators, then by using PI you can add only one extra integrator. Remember, by using PID controller you can add only one extra integrator, that's all. Okay, so if with that integrator also error is not getting reduced, means no, we can't do anything. So you need to assume you have a type 0 system. By adding one integrator for a step input, you can make the error 0. But the same system, if you apply a ramp input, error cannot be made 0. Okay, right? You should not perceive this problem as a universal. That means you should not make a wrong conclusion that if I use integrator, always error will be equal to 0. Only the situation will tell you. That's why the steady state error analysis already given how many number of integrators you need. So with a PID, you can add only one. If the system is having enough number of integrators, then if the total including integrator, that is a PID controller plus system, if total integrators in the loop transfer function is 2, a ramp input will make error 0. If total integrators in the system is 3, including PID controller, then the error will become 0. That's what the steady state error analysis concept. So go by this. Okay. Yes. Anyway, the right conclusion is for this problem, perceived in the right way, you have to give the answer. Okay. It eliminates steady state error. Okay. So by adding integral action, always the stability of the system is getting decreased little. Okay, so that is going to increase, that means not improve. It is going to make the transient performance little worse. Okay, so it is because of the stability is getting decreased. That means you can feel like a friction is getting decreased. That's a drawback of integral action. Integral action will reduce or will degrade the transient performance. Okay, it will make oscillations a little more in the system, but still it is going to eliminate your error. In fact, what is going to happen because of adding PI, your system order is going to get increased. Assume your G of S, H of S is a first order. If you add a PID or simple PI, okay, PI is a first order, it is going to present a pole, okay, at origin, means your system is going to become a second order. And since placing the pole at the origin is always contributing for decreased stability. Okay, so what he's talking about here, in advantage of integral controller only is talking about. Okay, so its drawback is decreasing the stability. So anywhere he mentions, so it is not going to make the system completely unstable. That is not the advantage. Okay, it's a drawback. Okay, it may make the system unstable sometimes, and definitely it is not going to make the system stable. Increase or decrease amplitude. Okay, so that's not the role given to the integral action, I action. So the role given to the I action is eliminating steady state error. Okay, yes, that's a correct answer. And hope everyone given the right answer for this as well. Okay, because it's very easy problem. Once you know the purpose of I action, then that's a way to give the answer for this problem. Next one, also from control systems. Yes, so the addition of a pole, that's what we have done. There we have added a pole at the origin. Okay, the integrator added a pole at the origin. Okay, pure integrator means a pole at origin. So this is also talking about addition of pole. Okay, something related to the last problem. Yes, let me uniquely give the answer for this. The addition of a pole to the open loop transfer function generally has the effect of, okay, say for example, I have a closed loop control system. Take some example and play with that. That's my system. Assume it's unity feedback. Yes, you need to have some concrete proof before going for the answer. So then you can give the answer confidently. Say, for example, I have 1 by S plus 2. That's my system. Unity feedback. Okay, yes. So the addition of pole to the open loop transfer function generally has the effect of what? So he's talking about the bandwidth, increasing the bandwidth of the closed loop system, decreasing the maximum peak overshoot, decreasing the bandwidth of the closed loop system. So he's talking about bandwidth and peak overshoot. Okay, so two things he's talking about: bandwidth and peak overshoot. So the pole is already there at -2. One pole is there at -2. Let me add one more pole. Say for example, 1 by S plus 4. Let me add. This is the pole I'm adding. So pole at -4. And there will be some K. and you can set the certain k value for this. Okay, because based on the k only, what we talk about is open loop finite poles. So the closed loop pole positions will be somewhere. The root low C concept will say, okay, as per the root low C, okay, for any finite k from 0 to infinity, roots will fall anywhere in the root locus segments. This is your root locus 1, root locus 1, this is a root locus 2, that is k tend to infinity, it is going there. And then this is starting point of the root locus or root locus, so k equal to 0. So the roots will fall anywhere in the yellow marks given. Okay, that's a trajectory or locus for k varying between 0 to infinity. Yes, that's where you're going to get. Correspondingly, we're going to have a performance. So depending on the k, your system may be overdamped. System may be overdamped. Zeta greater than 1. Okay, I'm using zeta for the damping factor. Zeta greater than 1 over damped, zeta equal to 1, it's a critically damped. Zeta between 1 and 0, it's a under damped. Accordingly, it is going to have the performance. Okay, so he's talking about two performance. Peak overshoot is nothing but time domain performance. Bandwidth is nothing but the frequency domain performance. We should connect it. So addition of the pole to the open loop transfer function generally has the effect of what means. Okay, so if it is a first order, we should not talk about the peak overshoot. Okay, so if it is a second order, we can talk about the peak overshoot. So then you can think about the bandwidth first. So decreasing the bandwidth or increasing the bandwidth. No change in bandwidth is a wrong question because the frequency response definitely will change for the loop transfer function. So let me, since three options are given for the bandwidth, let me first talk about the bandwidth, then we'll connect it to the peak overshoot. We'll see which is the correct answer. So without adding a pole, with g of s, h of s will be equal to 1 by s plus 2. Then set s equal to j omega. So g h of j omega will be, is going to be 1 by j omega plus 2. It can be written as, you can take the gain as 2s, the gain that is off. Rest will be 1 plus j omega by 2. The cutoff frequency is, it's a low pass system. Low pass, like a low pass filter, it's a low pass system, first order low pass system. So then the frequency response will be like this. So the gain will begin with off and the cutoff frequency is going to be, so asymptotic Bode magnitude plot, the cutoff frequency is the pole frequency, that is at 2 radian per second. That's how we get bandwidth means up to 2 radian per second. That's your omega b, we can say that's a bandwidth frequency. So 0 to 2 radian is your bandwidth, okay, for this low pass system. Now if g of s, h of s, if I'm adding a pole at s equal to -4, then s plus 2 into s plus 4 means, then we'll see what will be the bandwidth of this. Then set s equal to j omega. So then g h of j omega becomes 1 by j omega plus 2 into j omega plus 4. So then the gain will become 1 by 8. Then the rest will be 1 plus j omega by 2 and 1 plus j omega by 4. You will get two corner frequencies. Then if you refer the Bode plot for this, the gain will begin with 1 by 8. Then till 2, it is going to be the same. Then after that, it will fall at a rate of -6 dB per octave. Okay, then it will change its slope to -12 dB per octave. Okay, but it's approximate. Okay, this is the frequency 2 and this is the frequency 4. Okay, so this is how it goes. Okay, so the bandwidth. Okay, earlier the cutoff frequency is 2. So depending on where you place it. Okay, so the first one is the one influencing the cutoff frequency. Second one. Okay, so it's like two low pass systems in cascade. So this is one low pass. This is another low pass. This has a cutoff frequency of 1 by 2. This has a cutoff frequency of 2. This has a cutoff frequency of 4. Means when two low pass systems in cascade, and then I can take the minimum as the cutoff frequency, 2 as the frequency. Suppose it depends on where you add the pole. Okay, if it is s plus 1, that itself is going to become a cutoff frequency. Okay, so it depends on your pole location. So the point is the bandwidth is definitely getting influenced because of adding this x top pole. Okay, where you add that pole is very important. Okay, without that we can't say. So increase in bandwidth of the closed loop system, decrease in the bandwidth of the closed loop system. No comment, because where the pole is getting added is very important. Okay, so the overall frequency response you need to calculate. Say for example, if you go for the overall frequency response, then the overall frequency response for this will be, okay, the gain is changed. Okay, instead of having a DC gain of half, it is going to begin with a DC gain of 1 by 8. Assuming you are doing this without changing the gain means, then you can do like this. Assuming without changing the gain means, I can say it is 1 by s by 2 and s by 4 without changing the gain. Assuming, then we'll see how the bandwidth is getting influenced, if that is the one. So in this case, the frequency response will be like this. Asymptotic will be, it is beginning with 1, then there is 1 means it is 0 dB. Actually, you have to take, once you go with the roll off rate of minus 6 dB per octave. So it is 0 dB. The plot will begin with 0 dB up to it is 2. Then after that, it is minus 6, and around 4, the slope will change to, it is minus 6 dB per octave. And this will be minus 12 dB per octave. That's how it is going to change. So anyway, the cutoff frequency is going to be still 2 because the pole is getting added. So with the asymptotic Bode version, we can't conclude. If you go for the actual version, you may have a good chance to conclude. So if you go for the actual version, GH of j omega modulus of GH of j omega. If you plot this with respect to omega, this will be 1 by root of 1 plus omega by 2 the whole square into root of 1 plus omega by 4 the whole square, like that you will get. And if you go for the frequency response, then the frequency response will be like this. Okay, so during high frequency, it will be having a roll off rate of minus 12 dB per octave, because it becomes a second order. It becomes a second order. So the actual cutoff, so if it is only 1, it is contributing. So when omega equal to 2, it is contributing 1 by root 2. So it's omega equal to 2 means it's contributing 1 by root 2. At omega equal to 2, what does this contribution means? So at omega equal to 2, we'll end up with 1 by root 2. This will contribute root 2. This will contribute 1 plus 2 by 4. That is 1 by 1 plus 0.5 the whole square. So this is going to contribute 1 by root 2 into root of 1.25. You will get, that means the overall denominator is root 2 into root 1.25. Root of 1.25 will be greater than 1. Therefore, denominator will be greater than root 2. That means your cutoff frequency actually will decrease. That's where we are going to get 1 by root 2. So then I can say that, so addition of the pole may definitely influence the bandwidth. So it will decrease the bandwidth. So now we got a material to conclude. It is going to decrease the cutoff frequency, actual cutoff frequency, when irrespective of where the pole is. Okay, suppose if you have the pole, okay, here, so this is the pole arrangement, one pole at -2, you are introducing a pole at -4, you think of adding a pole, this is the pole at -2 means you are adding a pole at -1 means, yes, that is also going to contribute for decrease in bandwidth. So decrease in bandwidth is a good solution. Okay, right, that's one perception. So decreasing the bandwidth of the closed loop system is a ideal solution. Okay, so the overall gain is going to decrease. So he's talking about the closed loop system, but what we are talking about is only G of S, H of S, that is a loop transfer function Bode plot, but he's asking us to comment on the closed loop system. Okay, so what will happen to the closed loop system bandwidth? It's an open loop system bandwidth we are talking about this. Okay, what is a closed loop system bandwidth? So because of adding a pole. Okay, so you have to view like closed loop system, C of j omega by R of j omega modulus, that's a closed loop system. Then it is going to be G of j omega divided by 1 plus G of j omega. You take this modulus, take this modulus. Okay, that's a magnitude. Yes, what is happening? G of j omega bandwidth is changing. Okay, that is the gain is decreasing. So this gain is 1 by root 2, for example, means it's 1 by root 2, 1 plus 1 by root 2, you can think. Okay, so we need to have a material. It may look getting complicated. Yes, that's a way. 1 by root 2 divided by 1 plus 1 by root 2 means what do you get? 1 by root 2 plus 1 will be the resultant. So that means the gain is further decreasing. The gain is further 1 by root 2. So root 2 plus 1. Yes. So the gain is further decreasing. The bandwidth clearly decreasing. Okay. Adding a pole, decreasing the bandwidth. Okay. Yes. That is a best possible answer for this problem. Yes, we have to see the problem in another perception, decreasing the maximum peak overshoot. Okay. So if it is a first order, initially there is no overshoot. Okay, then second order means then only we can talk about the overshoot. So then if you talk about this, then you have to consider already a second order system like this. Already you have a second order system. There is a underdamped that is going to have the maximum peak overshoot. Okay, so MPO we can say. So the percentage MPO, hope you remember, that is e power minus zeta pi by root of 1 minus zeta square. We can play with that into 100%. That's a percentage overshoot. Adding a pole here, what will happen? Okay, adding a pole will create the repulsion. So it will start moving this way. So if it start moving this way, for example, for a K, so play with the root lossy concept. So the poles are repelling the two root lossy means then for a given K, without this certain root lossy you will get, with the pole you will get different root lossy. Okay, without this pole the roots will move this way. Okay, with this pole effect the roots will move this way. That means roots are moving closer to the geometric axis, means damping is getting decreased. As the damping decreases, actually the overshoot will increase. Okay, overshoot will increase. So this is wrong statement. Even with the perception given, assuming already you have a second order system with a finite peak overshoot, you are adding a pole means overshoot will increase, not decrease. So C is definitely wrong option. So in all aspects, D is the correct answer. Okay. So yes, let me conclude this session. Okay, with this problem. So thanks for watching. We'll meet in one more video. Thank you.